How is it different from what we've been doing so far? I'm just going to try to get this working. When I say circuits, what do you guys think? Resistance, what does that mean? When you say resistance, so we have circuits. In a circuit, we have resistors. What else? Yep, close. What is flowing through the wires when you have it? Electrons, or we have another way of measuring that? Charge, coulombs. So charge and coulomb, same thing. So yeah, we have charge per second, coulombs per second. So it's actually basically the speed of the electrons moving through the wires. It's not a distance that they're traveling, but it's the number of electrons that are being discharged. Now, let me just get this working. My I timed out for having been inactive for too long. And I'm also connected to the wrong Wi-Fi. Connected. And we can. My Adobe Connect just got reset, so make sure that you change that. You have to refresh the page. And if I'm going to connect here, oh well. Port 2. There you go. 1902. No. Nice. Sorry, just give me one moment, guys. Okay, I just have to restart that, and then we should be good to go. So when we're talking about currents, when we're talking about circuits, we're talking about a current that's traveling. Otherwise, going to be that you're not dealing with a static charge. So remember, if we're dealing with non-static electricity, electricity always needs to be flowing. Okay, so if I have a current, and I'm going to just draw a little wire here. So if I have a current, and there's a certain amount of things that are happening there, I drew a squiggly line, but it could literally be anything. Is it possible that the charge gets blocked somewhere? So I have the charge that's traveling through my wire. Is it possible that the charge gets blocked somewhere? How? What is it getting blocked by? The physical block? There might be a resistor there, but I'm talking about if there is no resistor, would there be something there? Can it stop? Remember, we're talking about kinetic electricity. Kinetic means moving, exactly. So can it stop or not? Cannot stop. All right, now that I've restarted this, I should be able to connect. Oh la la. Hmm. It's not working on the day. That's weird. You can see my screen on the computer, I know, but I wanted to project it here as well. And it's not letting me. Oh, here we go. Search or enter. This might be the thing that works. 1.0.2.42. Okay, I can't use it for some reason. It's giving me some issues. You guys can see it on your screens though? Not anymore. Weird. There you go. Now you can see it. Okay, perfect. So we're going to continue from there. Not sure why it's not working. I have to ask JP to come take a look. But here is the circuit. Looking at the there. The one I'm showing you guys on the screen right now, this first one. This circuit is what you guys are going to need to analyze by the end of this unit. Joe? No, you don't. But it is a picture of a circuit, and it does represent a little bit of what you guys are going to be seeing. And circuits can be this complicated, okay? If you look at this diagram, is there anything that you recognize? You see a bunch of lines? Yeah, okay. Yeah. There are resistors. What does a resistor look like? Yeah, like a little squiggly line. Do you see a lot of resistors? Yeah, there's a lot of resistors. I'll just circle a couple of them, like this one here is a resistor. That's a resistor. What else do you recognize in this circuit? Yeah. Where? Yeah, exactly. So there are capacitors. So I'll circle one again. Whoops, let me just go back. There's a capacitor there. You want to connect to this? Si puoi just aller sur un site web. Ah, d'accord. Est-ce que tu peux aller sur le réseau GET? Ah, il y a un mot de passe. Vous n'avez pas reçu un mot de passe, hein? Okay. You guys have a password for the guest network? There's no password usually, but they're asking for one. Okay. Daniel? Okay, d'accord. So, okay, yeah, so there's a bunch of stuff that you see there. Can someone identify a voltage source for me? What does a voltage source might look like? It looks maybe like a capacitor, but the lines are not the same length. You can see maybe an example of that on the screen, on the whiteboard. Or does anyone see a ground anywhere? What's that? For a battery? No, that's it's not the same length. It looks like a triangle, kind of, like they get smaller and smaller. Yeah, but it is 4 lines. Yeah. That would be that's an example of a capacitor right there. Yeah. Are you looking up the answer for the test? You're still thinking about it. Okay, let's move on. Okay, in essence, that's what I mean. These are what the parts of a current are, of a circuit is. We're going to go over what a voltage is. We're going to go over what a resistor is, capacitors, how they're used, and where you see them in real life. In order to understand them, you need to understand that the current flow. That's the most important part. Here's something very strange. When we started talking about this, did we say that protons can move? In general, protons don't really move because they're a part of matter. And what's going to be, if there's going to be a flow in a circuit, what's going to be the thing that flows? Electrons. However, we didn't know this a long, long, long time ago when we described the first circuit. when we described the first circuit, we said that it was the positive charge that moves along the circuit. So we have a positive end here and a negative end here, right? And we said that it was the protons that were moving out of the positive end of the battery or the voltage source or whatever, and that it was traveling across and doing all the work. Well, the answer to that is we were wrong all along, but we've done it so much so that we just kept it that way for convention's sake, right? So while you should know that it's the electrons that are moving in this direction, when we're talking about circuits, we're always going to assume that it's protons moving in this direction. Okay? We good with that? It's counterintuitive, it's stupid. That's because scientists are lazy and we don't want to go back and change every textbook known to man. All right, so that leads to Kirchhoff's rules, and then you should be able to describe what Kirchhoff's rules are at the end of this. There are a couple of them. So if we come to the first circuit that I show here, how could you guys describe it for me? It's a parallel circuit. So how did you know it's a parallel circuit? A node, exactly. Sorry. There is a node, okay, and I'm going to circle them. So here's a node. 2 and 7 are nodes, and 3 and 6 are nodes. Would you say that 4 and 5 are nodes as well? No, 4 and 5 are not nodes, right? Because if you're a current and you're coming in this direction, then you have nowhere to go but downward. Okay? Did you guys get it to work? It works? Ça marche? Ah, c'est un connexion. OK, donc il faut aller sur Adobe CNN. Ouh, le clavier est un peu bizarre pour moi. Ah, le Q avec le A et qui change avec le Z qui est là. Le période est où? Le point? C'est lui? Oui, mais. Ah, OK, ouais. Adobe CNN. Comment est-ce qu'on fait un slash? OK, d'accord. NYB 0. C'est toi de temps. Vraiment, le clavier, c'est comment ça le français? Juste mettez votre nom. OK, puis entrez dans la chute, dans la salle. Je télécharge? Oui. OK. Ensuite, ça devrait commencer. OK. All right, so moving on. What you have there at nodes 2 and 3 are choices. So if you're current and you're leaving the battery at the positive end, so you're going upwards, all right, and you need to go along the wires, so those lines are wires. At node 2, you have a choice. And that's what makes this a parallel circuit. The choice that you get from going down that first branch or continue along to go to node 3. All right, and that's what's important in parallel circuits. I want to also point your attention to that battery. How do you think of that battery? Yes, Elizabeth? Yeah. There's a website to go to. It's did you bookmark it? It's not there. You got to book. You have to have bookmark it. Here, it's Saint Anne dot Adobe Connect. Go all the way to the end. Actually, it's where the end of that one. Yeah. It's Adobe. Yeah, there should be no one who's using that. I thought it's a public one. Est-ce que tu es à la bonne place? Efface tout ce qui est après le point .com. Fais NYB. Slash NYB 01. 0, 1, pas O1. Is everyone getting it to work? I wish I can get this to work because it's really bugging me now that it's not working. Okay, let's continue. So you have our circuit that is allowing a current to go through, and what's going to happen is you have a node and you have an option. All right. So the option is going to be to go on to node 3 or on to node. So here you have a node. You can go down or you can go to the next node. If your current's coming in this way, the fact that you have this option makes it a parallel circuit. If you had no option, it would be a series circuit. Okay. And these nodes are super important because there is a voltage across them. So now you guys have to remind me because the term voltage comes up a lot in circuits. You guys just had a test on it, so I know you guys know what you're talking about. So voltage, define it for me, and then we'll try to apply it to what it does in a circuit. What does a voltage mean? Energy per charge, okay, and how else could you define it? Like if you were to take, let's say that again. It is work per charge. It's the potential energy of a substance per charge. Yes, Elizabeth? So work needed to make what move? Or any charge move, okay? And so it's a measurement of energy, right? Okay, so if it's a measurement of energy, then you can consume it, you can absorb it, right? It never disappears because of conservation of energy, but it does get transferred into other things. So now if you have a voltage difference, right? So if I have this, I want you guys to look at that circuit. So it's going to be on the slide before this. Before this, yeah. If you look at that voltage, it says 6 volts. That means that from the top of that circuit, all the way around and back to the battery on the other end, there's going to be a potential difference of 6 volts. All right, so if there's a potential difference of 6 volts, what happens in an electric field when there's a potential difference and you put a charged particle there? What's going to happen to the charged particle? It moves, all right, and it's going to move along that wire. That battery is not going to allow you to have any internal movement of charges, all right? So between that 6 volt and that 0 volt line, so this was 6 volts and this was 0 volts, right? There is no movement between those two directly. It has to go, the charge has to go all the way around the circuit and then come back. If I had a stream, and this is how electricity works in everywhere in Quebec, if I had a stream of water coming downhill, it has a certain level of what at the beginning? Potential energy, and at the end it's got a certain amount of kinetic energy. And in Quebec, how do we use that system to generate electricity or energy? What's that? Say that again? The barrage, which is, yeah, turbines, and the turbines are located in dams. So the gravity is going to cause this, the potential gravitational energy is going to cause the water to flow down, turn a bunch of wheels, and those wheels are going to create energy for us and then fall downwards. We didn't have to do anything because gravity did everything for us. We basically got energy out of nothing. That's not true. We use that potential energy, and some animals are suffering because we've disrupted their ecosystem. But for the most part, it's a pretty clean source of energy. It's the same thing here. If you have a potential at the beginning of 6 volts and you have a charge that's going all the way around and it's gaining kinetic energy to go through to the other side of the current, to the other side of the circuit, then it can do some stuff along the way, right? And what are those kinds of things that a charge might do along the way in a circuit? Okay? Light up a light bulb, run your computers, do anything. Basically, that's what circuits are. That's what electricity or electronic boards are. All right. It's that this charges have this potential energy at the beginning. They get shot across the circuit because that's the only way they can get to the 0 volts on that other end of the battery and have consumed some form of energy. Okay. So far, so good. Okay. So we have to talk about Kirchhoff's laws. And Kirchhoff's laws are quite simple when you think about it, but very confusing when you combine them all together. So we're going to go through them one by one. And the first one we're going to talk about is for parallel circuits. So the rule is that the amperage gets to split up whenever there is a node. So I'm going to draw an example here. So if I have a current coming in that direction, right? And then that current gets split into two different directions, and we call these I1, 2, and 3 respectively. What could you tell me about I1, I2, and I3 mathematically? Yeah, exactly. I1 has to be equal to I2 plus I3. That's Kirchhoff's first rule, all right? If you had no node, and you had only one way to go, so this is a series circuit that I'm drawing here, what could you say about I1 and I2? They're equal. There is no splitting of the current. Okay? So here you can say that I1 is equal to I2. That's kind of intuitive, all right? So that one is an easy one to remember. I want to give you guys an analogy that I came up with yesterday. I am super proud of this analogy. Yeah? So imagine you have, and as silly as this sounds, imagine you have a Girl Scout company. Okay? So you're responsible for organizing your Girl Scouts. You guys all know what Girl Scouts are? Okay. So you organize your Girl Scouts, and they have to go out and sell cookies to raise money for a foundation. Okay. So you have them all around you. You give them each 100 boxes of cookies, and you say, go on and sell these cookies, and then come back later. So ideally, these Girl Scouts would leave your headquarters, right? Go spend all of their cookie boxes or sell all their cookie boxes, and then come back with no cookie boxes. That's exactly how it is in a circuit. So you start off with a certain amount of charge slash Girl Scouts, right? And these Girl Scouts go out, they sell their cookies, or they give off their energy, or in this case, we're going to call that potential or your voltage. They're going to lose their voltage, and when they come back, they should have 0 voltage. Okay? Now, if you're a Girl Scout, and let's go back to this circuit here, this one here. If you're a Girl Scout, if you're one Girl Scout, which path can you go down? And can you go down all 3? What's that? You have the choice of going down all 3, but once you go down one, you've gone down that one. Okay? So that means that if you're a Girl Scout at here waiting to go down, or a Girl Scout here waiting to go down, or a Girl Scout here waiting to go down, you can choose one of those, but as soon as you pass through one of those houses, you're going to have sold all your cookies, and therefore you have no more voltage. So the voltage difference across these nodes in a parallel circuit must be the same. If you had 100 volts before, then you will have sold them after, right? If you have 100 volts before going into the house, and then after coming out of that house, you have no more cookies, then you've spent all your voltage. You can't go through all those houses because each one of those is going to buy your cookies, and you're just not going to have enough cookies. Silly analogy, I know, but it works. I had to have Mr. Rakarski's slides, and you'll see at the end of this that his analogy had to do with soldiers and bullets. It was kind of depressing. It was like soldiers go out to war, they all carry ammunition, they go shoot all their bullets, and then they come back. And then you run into the situation where a student lifts up their hand and goes, well, my parents died in war and they never came back. And then the whole thing is garbage and you can't talk about it. It's kind of macabre, so I chose not to talk about it. And then I talked about it, and now it's depressing. So, so this is exactly what I was saying in the Kirchhoff's second rule, is that the voltage, whoa, what's going on out there? Who was that? The excitements of going to chem class, I suppose. So yeah, so the voltage across each of those parallel parts of a circuit are going to be equal, right? So think about it with the cookies. No matter which house you go through, which path you take, you still only have a certain number of cookies that you can go through those houses. So that means the voltage is going to be constant in a parallel part of a parallel circuit, okay? And this is the tricky part. It's the opposite for series. okay? In a series circuit, the currents don't split up and the voltage does split up, okay? So I'm going to draw you guys a little circuit here. We're going to use the cookie analogy. So I have a circuit there, and you have a certain, you're a Girl Scout, you're leaving the battery, you're going in the upwards into the right direction, right? And you have 100 cookies, but you know you have 2 houses to go to. So if you know you have 2 houses to go to, then you're not going to spend all your cookies at once. So you're going to drop some cookies at the beginning. So you're going to lose some voltage in that first house. You're going to lose some voltage in that first location, that first resistance. And then you're going to lose the rest of it on that second one. So let's say you start off with 6 volts and each of these resistances are equal, then you're going to lose an equal amount of voltage for each one of those resistors. So you would lose 3 volts of the first one and 3 volts of the second one, so that when you get back to the battery, you have no volts remaining, all right? That having no volts remaining is going to be key to this unit, okay? Yeah. Exactly, yeah, okay? Any questions about this? So far, is this review? Good. All right, it should be a review. It should be very familiar to you guys. So I have a circuit here. It's a series circuit. And assuming that I have a 12-volt battery, what could you tell me about the voltage across each of these resistors? Yep. The voltage is going to progressively go down because at each stop you make, you're going to lose more energy. All right. And if they're all equal, all the resistances are equal, they're all R. So what could you say about how much voltage you're losing in each resistor? Yeah. Exactly. You're losing 3 volts in each resistor. And if you lose 3 volts in each resistor, that means you come back to the battery at 0 volts. And that's key. Again, remember, when you come back to the battery, you have to have 0 volts. What if I made it a bit more complicated? And it's really not that complicated. I had a 6-volt battery there, let's say, and that leads you to a resistor. And then you get into another battery that gives you another 6 volts, and then you go down into back to the battery after passing through a resistor. What do you think is going to happen there? What do you think is going to happen? Yeah, voltage adds up. All right, and is that exactly what Zachary said as well is right. So imagine you're a Girl Scout. Yeah, Cedric, imagine you're a Girl Scout. Yeah, so imagine you're a Girl Scout and you're moving along, you give all 6 volts to that first resistor, you get back your 6 volts from that second battery, you go through the rest of the circuit, and you spend the rest of your 6 volts there, and you end up back at the battery at 0. Okay? So remember that each end of the battery, in this case, you need to have 0 volts going into it, 6 volts coming out of it. Okay? You guys understand it so far? Okay. So I have some practice here. You know what? Actually, I'm not going to do this because I'm actually going to move ahead. We're going to skip over this problem. We're going to come back to it afterwards. We're going to go straight to equivalent resistances. Again, this should be review. Have you guys done this in high school? Where you had to add the resistors together on a series and a parallel? You guys have to do that? You guys remember that? So it's not so hard. It's pretty straightforward. You have to know that an equivalent resistance is the sum of the resistors, right? So that you could break down any complicated circuit, you can break it down so that it could only have one resistance value. This is how you would do it. So if you had resistors in series, so for example here, look at how these resistors, these 5 resistors, they're all one right next to each other. There is no option for the current to go anywhere else. It has no choice but to go pass through right off through all 5 of those resistors. it would be the same as going through one equivalent resistor, and that's what an equivalent resistor means. In the case of a series circuit, it's very simple. You just kind of add them up, right? So the Req would be equal to the sum of all the resistances I. Did you guys learn summation notation with the sigma? Okay, good. Req is equal to the sum of all the resistances I from I is equal to 1 to n. Okay? That's pretty straightforward. You guys remember that? So here it is. If I had to ask you for an equivalent resistance for this circuit, what would you tell me it is? R. Yeah, very good. So here Req is equal to R plus R plus R plus R, otherwise known as 4R. Okay? In parallel, do you guys remember this relationship? So you can say that 1 over Req is equal to the sum of 1 over Ri from I is equal to 1 to I is equal to n. So for a second, Ri is you can say that is the first resistor. So it would be this would be nth resistor, and Ri would be the first resistor. So it's the sum of every single resistor from R1 to Rn. Down here, you can see a bunch of examples of what a parallel circuit might look like. You don't always see it the same way. Sometimes they draw it in the most confusing ways. It's your responsibility to try and unconfuse those certain circuits. There's going to be an example of this coming up. Let's do these simple ones first. So the idea is that you have a voltage source, and that's going through this parallel and series circuit. And we want you to find what is the equivalent resistance for this circuit, all right? And the trick is to always break down the most divided resistors first. So like here you go. You go along this way. Your Girl Scout has the option to going left or right at that first junction. You can go left or right. If you went left, you go down this resistor, and you can now choose another option, left and right. And then once you choose your last option, you get to go back. So that last option is where we're going to combine first. Okay? So if I were to take these two parallel resistors here and I have to combine them, how would you do that? Are they in series or in parallel? They're in parallel. Okay? So if they're in parallel, I have to add them up by going 1 over 30 plus 1 over 45 is equal to 1 over R. Can someone do that and give me a number? It would be 3 over 45, so 1 over 15. 1 over 18, and then the answer should be 1 over that, right? 18. Okay. So the resistance, the equivalent resistors, if I had to knock out those two resistors and replace it with one resistor, I would be able to replace it with a 18 ohm resistor. Okay? Now check it out. I got these two that are in series. that 42 ohm resistor and that new 18 ohm resistor, now those are in the series. I can add those two guys up. So how do I add those two up? You just add them. So what's 48 plus 12? Come on, guys. 60. All right, so 42 plus 18 is 60. So now you can replace all that. So I'm just going to erase it on mine so it becomes a bit neater. All right, I can replace all these resistors by one resistor that has a resistance of 60 ohms. Now I have the option of going to two resistors. I can go to that 60 resistor, I can go to that 40 resistor. That means these two are going to be in parallel. And if they're in parallel, I need to add them up using the inverse again. So 1 over 60 plus 1 over 40 is equal to 1 over R. And what would that be? $24? Okay, so R is equal to 24. That means I could reduce this circuit. I have a voltage that starts at A, it goes through one resistor, ends at B, and it's the same thing. You can go through this entire circuit, and resistance-wise, it would be the same thing as going through just one 24 ohm resistor. Okay? And it's really, really, really important to be able to do that. We won't learn that part today, but I'm sure you guys know how to do it current. So we'll figure it out. Okay? 24 ohms is that one resistor, the equivalence of this circuit. Here's a second example. This time I want you guys to do it on your own. Find the equivalent resistance. It's a bit more complex. If you're done that one, there is a second one after that. I want you to work on that as well. Okay? So I wanted to show you guys something. Normally, I would have it projected on the board, guys. Pas un mot d'anglais, c'est pas grave.
Non, mais c'est.
OK. Donc, qu'est-ce que normalement, je vais projeter mon leçon sur le tableau, de plus sur l'écran ici. Normalement, j'ai des classes plus grandes. J'ai une classe de 26 élèves. Donc, les élèves qui s'assoient ici ne peuvent pas voir, ou même s'ils s'assoient ici, il y a un... Pardon? Exactement. Donc, eux, ils se passent de la mauvaise sens. Donc, c'est important d'avoir accès à ce que j'écris sur mon écran pour qu'eux, ils voient la même chose sur leur écran. Pour l'instant, oui. Ensuite, on va faire des circuits et tout ça. Ça va être plus informatique. Oui. Ouais, c'est vraiment cool. Une autre chose, c'est que j'utilise un programme qui s'appelle Snagit. Okay? Tu peux voir ici, je vais peser le